This is the Chapter 18 video for sampling distribution models. Let's get started. Now, yesterday and the day before, I was talking to you about the normal model and how the normal model is going to be our best friend from now until the end of the book, pretty much. Well, to use a normal model, we need to specify two parameters, its mean and standard deviation. Which normal model is the right one? Well, the center of the histogram is normally at P, so we'll use mu, the mean of the normal model, at P. And again, here's what our normal model looks like. And here before we used to have mu, like in chapter 6, we'd have mu here at its center. And now at our mean, we have P. Once we know the mean, P, we now automatically can calculate or also know the standard deviation. Now back in chapter 17, last chapter, we saw that the binomial model standard deviation was the square root of NPQ, where N is the number of trials, P is the probability of success, and Q is the probability of failure. And the standard deviation was the square root of the product of those three things. Now, we want the standard deviation of the proportion of successes, which we call now P hat. The sample proportion, P hat, is the number of successes divided by the number of trials, N. So the standard deviation must also be divided by N. So now the standard deviation of P hat, the proportion of successes, is equal to the square root of NPQ divided by N. And that simplifies to just be the square root of PQ divided by N. So now we have a new standard deviation. And this deals with categorical data, and we'll get more back into that later on. So let's say now we have a population, and we draw random samples, simple random samples from that population of n individuals. The proportions we will find will vary from sample to sample. So let's say that I take 2 dice and I roll 2 dice. Those 2 dice add up. We add the whatever the values are. Let's say we got like a 5 and a 4. You add them, so you get 9, and you divide it by 2 because there's 2 dice, and you get 4.5. That proportion, or that average, that mean, is the sample's mean. Now, if we take another sample, so take the dice and roll them again, and let's say I don't know, get a 1 and a 2, that sample, the next sample, should have, oh, maybe should be, definitely varies from the previous sample that we just did. And hopefully it makes sense to you that the proportions that we'll be getting, those averages, those means that we'll be getting from sample to sample must vary, should vary. Now we can model the distribution of these sample proportions with a probability model. And hopefully you see here that it is definitely normal. And but now you see as we see our normal model here, we have a capital N, whereas before we used to have mu comma sigma as our normal model. Now we have capital N is equal to P comma the square root of PQ divided by N. And again, down here, if you see here, the mean is at P, and one standard deviation away from P is 1 times the square root of PQ divided by N, and then 2 standard deviations again is 2 times the square root of PQ divided by N, and etc. So we have our positive first, second, and third standard deviations away, and our negatives. So again, talk about the die roll. Let's take a look at what a simulated look at 10,000 die rolls would look like. So I did this using simulation, and my 2's didn't come out as much as the other ones did. It's just slightly little less, but hopefully you see here, it is unimodal, but more importantly, it is almost uniform. Now, granted, if it was truly uniform, like if it all was the same, it'd be most theoretical, and that doesn't really mean much to us because it doesn't have any variation at all. But in here, we do have some variation, which is good. It's nice. Now, if we have one die roll, we can't really take a mean of that single value, so that's why we have this uniformity. But when we take two dice and then average the values that you get when you roll them and do this 10,000 times in simulation, we get something very different from the first distribution. This distribution, as you see here, it's nearly centered on 3.5. And again, I would imagine it makes sense. The 7 would come up the most often. The probability of a 7 coming up in two dice, when you add them together, is the most. The probability happens the most. And 3.5 here would happen the same way. And then like vice versa, a 1, aka a 1 and a 1 coming up in two die is very small compared to the 7. And same thing with a 12, a 6 and a 6. So let's take a look at 3 or even 5. So in the 3, that means you take 3 dice, you roll 3 dice, you take all of those values, divide it by 3, so you're averaging those values. And take a look at what this distribution looked like when we simulated it. And notice its shape. And then again, look at this one here where we look at 5 dice, where we roll all 5 of those dice, take all of those numbers, add all 5 of those numbers, divided by 5, and again, average those values, and here is those distributions. There's average, those mean distribution. Now hopefully looking at this one versus the other that I showed here with 2 dice versus 3 dice versus 5 dice, hopefully you see what the shape is nearly looking like. Hopefully you see, yes, again, they're becoming more bell-shaped. So it's approaching the normal model. And that's exactly what we're trying to show here, is that the sampling distribution of any mean becomes more nearly normal as the sample size grows larger. So how do we make sure that we're using the normal model in the correct manner? There are some conditions that we have to follow. So the distributions of sample proportions or sample means, and there's some conditions. There's 3 that we must look for. And I'm going to pause here. We're at our max time, so I'm going to pause here. We'll go on to the next video in just a moment.